everyone, it's Wednesday, which means it's time for another Chem Help ASAP live stream. So hello to everyone who's joining us right now. Hello to Jessica, I saw that you logged in. So tonight we're doing sometimes the dreaded, but we'll get through it, Lewis structures. So just like I try to always do, we're going to start with the very simple and we're going to work our way up to the more complex structures. So let's go ahead and jump in. And of course, if you have any questions during the stream or you want to see another example or you want to see something in, just please let me know in the comments. I'll keep my eye on what's going on. All right, so Lewis structures. Before you can do Lewis structures, you have to have an understanding of electrons, and specifically you need to be able to identify valence electrons versus core electrons. Okay, so let's just get some definitions first. All right, so your valence electrons are in your outermost shell. These are the ones that are going to interact with bonding, which is why we're so interested in them. Your core electrons are basically everything else. They're much closer to the nucleus. They are not going to participate in bonding unless you're doing something really, really outrageous. So let's go ahead and just identify core and valence electrons of some elements just so we get some practice doing this, because we're going to need to do this for our later problems. So the best way I think to identify your valence and core electrons initially is to do the electron configuration. So for example, let's do lithium. All right, so lithium is right here, atomic number 3. I'm just going to write out the electron configuration. So it's going to be 1s2, 2s1. All right, so lithium has 3 electrons. 2 of them reside in the 1s orbital and 1 of them resides in the 2s orbital. So again, let's differentiate in lithium between the valence electrons and the core electrons. So your valence electrons, again, we said are in the outermost shell. So when you're looking at your electron configuration, you want to look for that inline number, the largest of the big number that is the largest. So we have a 1 and a 2 here. So we have the 1s and the 2s. Our valence are going to be in the 2s. So there is 1 valence electron in lithium and there are 2 core electrons. So I'll just write that down. So 1 valence and 2 core electrons. Let's just run through a couple more examples of this and then we'll get into other things. But this is really important to be able to understand, because if you can't count up your valence electrons, then Lewis structures are going to be just about impossible. So let's do an element that has more electrons than just 3. Maybe let's do bromine. Okay, so this is going to be a long one. So we have 1s2, 2s2, 2p6, 3s2, 3p6. We're going all the way to bromine, 4s2, 3d10, and then 4p5. And that gets us to bromine. Okay, so first, let's identify valence. This is why I like to talk about valence first. All right, so again, I'm looking at my, what I call my in-line number. So these are these numbers right here, not my superscripts, but my ones that are in line with all of my letters. And I want to find the largest in-line numbers. And I can see definitely here, I've got a 4. So 4p5, those are definitely valence electrons. But don't forget you have another 4, the 4s2. So you have 2 plus 5, you have 7 valence electrons. And all the rest are core. So for bromine, that's going to be 28 core. I'm doing my subtraction right from 35. Okay, so these are the valence electrons that we're most interested in because they are the ones that are going to do the bonding. And so they are the ones that are going to carry us through all our neutral atoms, and then when we get to molecules, these are going to be very important. Okay, so good, no questions on valence and core electrons. All right, Now let's talk about, now that we know what valence electrons are, there are patterns of valence electrons in the periodic table. So you don't have to always write out the electron configuration, although you always can. Let's find some patterns so that we can predict valence electrons a little bit faster and a little bit easier. So for example, let's maybe work down the first group. And so we're going to identify, really at this point, we're just going to identify valence electrons. We're not going to worry about the core electrons because they don't bond anyway. All right, so starting with hydrogen is really easy. It only has one electron, right? So that is its valence electron. So we'll say one valence electron. Okay, now just again, moving down the group, we're moving down the column. Lithium, which we've already seen, is 1s2, 2s1, and like we've seen, it also has one valence electron right here in the 2s. Okay, let's do sodium. This is going to be a little bit longer. 2s2, 2p6, 3s1. Again, one valence. All right, keeping on moving down the group, let's do potassium. All right, these are getting really long, so I'm going to use the noble gas shortcut. So for potassium, I'd use argon and 4s1. Now the nice thing about the noble gas shortcut is it pulls out not necessarily all of the core electrons, as we'll see, but it pulls out most of them. Again, potassium, there's your valence electron. It has one valence electron. So hopefully you're seeing a pattern here, right? Down this first group, how many valence electrons are in all of these elements? There's only one valence electron. So for rubidium, if you needed to predict how many valence electrons does rubidium have, I don't even need to write out the electron configuration. I'll tell you it's got one. Cesium has one. Francium has one. Okay, so we use these patterns to our advantage. Okay, let's do, so we've done our first group. I'm not going to go through all the groups because it's going to take forever, but let's do our second group and then maybe we'll do our halogens. Okay, so second group, let's start with beryllium. That is going to be 1s2, 2s2. Here are our valence. It's got two valence electrons. Moving on to magnesium. 1s2, 2s2, 2p6, sorry, 3s2. Again, two valence electrons. You probably know where this is going, but I'll go ahead and write out calcium. Again, I'm going to use the noble gas shortcut. That's argon. And then 4s2. Yep, you got it. Two valence electrons. All right, so at this point, let's take a guess. An educated guess. We know that there are one valence electrons in the first column. In our second column, there are two. So if we go here to column number 13, which again, so we go from our S's to our P's, guess how many valence electrons? You got it, 3, 4, 5, 6, 7, and 8. So before we leave this, just so that I can convince you that yes, this is correct, let's go through the halogens or group number 17. And I'm going to erase these guys right here, just so I can show you that, again, this does tie into the electron configuration, and I'm not just making this up because I want to. Okay, so starting with fluorine. So fluorine is 1s2, 2s2, 2p5. Again, if I'm counting up valence, it's going to be the 2 plus a 5. Here is my 7 valence electrons. Okay, switching over next to chlorine. Going back to my noble gas shortcut because these are just really long. That is going to be 3s2, 3p5. Again, you can see 2 plus 5, we have again 7 valence. And then for good measure, let's just do bromine just so I can really convince you that there are 7 valence electrons in all of the halogens. Although we already did bromine, but it's okay. Bromine, we're going to use argon, and then we're 4s2, 3d10, 4p5. Again, we've gone through these D's here in our fourth period, but they're not valence because remember the D's count back 1. These are 3 D's. Our valence are going to be the 4s and the 4p. So again, I have 7 valence electrons. Okay, so hopefully this makes sense. And again, if you ever forget the pattern, just run through a couple of electron configurations and hopefully the pattern becomes evident very quickly. Okay, questions? No questions. Okay, this is good. Hopefully this is really easy for you and we're ready to go on to the next step. Now we're going to do Lewis structures for neutral atoms. So we're actually getting to Lewis structures now. So for our Lewis structures for neutral atoms, again, these are just atoms. We're not to compounds yet, but I promise we will get there. We just need to know how many valence electrons. So let's start with our easiest. We'll start with hydrogen. Hydrogen only has one electron, so that is its valence electron. So we just draw one little dot next to hydrogen. That is the Lewis structure for hydrogen. Okay, let's go maybe oxygen. How many valence electrons in oxygen? Well, again, if you remember our pattern from back here, here's oxygen. It's got 6. You could always just count across here. 1, 2, 3, 4, 5, 6. That's another way to do it. So we're going to draw 6 dots around oxygen. Now, as much as possible, we like to keep our electrons in pairs because that is going to be useful later on. So my 6 dots, I'm going to draw in 3 pairs. Now, you don't have to do this, and sometimes you will see people who don't do this, but I think it carries forward into doing Lewis structures for molecules a little bit better because then you're used to keeping your electrons in pairs, which is something we definitely want to do. Okay, let's do another Lewis structure. Let's do the Lewis structure for barium. It is in the second column or the second group. It has 2 valence electrons. There you go. Just bam right there. So remember how last time we talked, I proved to you hopefully that all of your halogens have 7 valence electrons. So let's draw the Lewis structure for all of the halogens. Why not? So starting with fluorine, again right here, atomic number 9, it has 7 valence electrons. Again, I'm going to keep them in pairs as much as possible, but with 7, I have an odd number, so I'm going to have 1 right out there. Chlorine, it has the same number of valence electrons, so I am going to draw the dots around chlorine the same way I drew them around fluorine. So the point I want to make here, and I'll keep going, let's do bromine, is you don't have to memorize these. Maybe you memorize the pattern just so it comes a little bit quicker and a little bit easier, but I think students get stuck feeling like they have to memorize all of these Lewis structures. You don't have to memorize all these Lewis structures. Look for the patterns. Let the patterns help you. So that's bromine, and for good measure, let's do iodine. Oops, sorry, that electron got a little bit wild there. And for that one, I decided to put the unpaired electron underneath. Again, it doesn't matter. You can put it where you want, but I do like to, as much as possible, again, keep my electrons in pairs. Okay, so these are kind of our easy ones here. So we've done our core and valence electrons. We've counted them. We found our patterns. We have done our neutral atoms here. Now let's talk about what happens with ions, because now we start changing up electrons. Oh, check my mic. There's a slight clicking. Okay, so let me check my connection. Give me a second. Okay, so hopefully that gets rid of the clicking. Okay, good. All right, great. Great. I just pushed everything in a little bit more. Okay, that's neutral. Now we go ions. All right, so remember when you form an ion, you're changing the number of electrons. This matters for our Lewis structures because our Lewis structures show how many valence electrons. So let's do, I think it's easier to start with our anions. Let's start with fluorine. So when fluorine becomes an ion, it has a charge of -1. What does that mean? That means fluorine has gained an electron. It now has more electrons than protons. Well, if we go back to our neutral atom and we did fluorine, you can see fluorine has 7 as a neutral atom. So you're going to take the number of valence electrons that the neutral atom has, and then you're either going to add or subtract depending on if you've got an anion or cation, and that becomes your valence electrons. So for fluorine, It already has 7 valence as a neutral atom, but because now we have a charge of -1, it means we add 1 more valence electron. Does that make sense? Okay, so if I'm going to draw the Lewis structure for the fluorine anion, I'm going to have 8. And of course, this hopefully makes sense. This is why fluorine gains one electron, because then it has the same electron configuration as neon right here, which is a noble gas, which has a full outer shell or a full octet. We're going to see a pattern here. Okay, so that's fluorine. Let's do oxygen next. So oxygen, when it becomes an anion, it has a charge of -2. I should have maybe put the periodic table on this page, but that's okay. We'll just use this one back here. So finding oxygen, oxygen has 6 valence electrons as a neutral atom. So we start with our 6 valence. It has a charge of -2, meaning it has gained 2 electrons. So I'm going to add 2 more valence electrons. Oops, I didn't mean to make that mark. That's my bad. So again, we have a total of 8 valence electrons, which means I am going to draw 8 dots around oxygen as an anion. Okay, so hopefully you're seeing a little bit of a pattern here, right? Okay, let's do another anion. Let's see. Let's go ahead and do bromine. Why not? I'm kind of partial to the halogens anyway. So when bromine becomes an anion, it has a charge of -1. Looking back at our periodic table, bromine is right here underneath chlorine. So as a neutral atom, bromine has 7 electrons. So 7 valence electrons. And because it has a charge of -1, it means it's gained 1 electron. So I'm going to add 1 valence. So again, 8 valence electrons. Now, you can have anions that don't have 8. It's pretty rare that this happens. Again, when we do our Lewis structures of molecules, of course, we're going to follow the octet rule. Everything's going to have 8. There are exceptions to that. But this also applies to our anions and our cations. Remember, these elements are trying to work their electrons such that they get a full outer shell. So they want 8 in their outermost shell. They want 8 valence electrons. So we're going to see a similar pattern when we talk about cations. So cations, let's do sodium. So when sodium becomes an ion, it gets a charge of +1. So instead of gaining electrons, cations lose electrons. So this means sodium has more protons than electrons. It's lost 1. So if we go back to the periodic table, here's sodium right here. It started with 1 valence electron, but it now has a +1 charge, which means I subtract 1 valence electron. So there really are 2 different ways that you can draw sodium. Most of the time, you just leave it alone like this with no dots around it. But sometimes you will see that they will put 8 electrons around it. This is less rare. This is less rare. This is less common. This is more rare. You don't see this very often. So even though I wrote that in, I'm going to erase it because I really don't like it. So with anions, you tend to complete the octet. With cations, you tend to remove those electrons. So let's do barium. All right, so barium is right here. When it becomes a cation, it has a charge of +2 or 2+. Again, it starts with 2 valence, but then it loses those 2 valence. So we just leave it as is, just like this. Again, so barium and sodium, and you can see this. So here's sodium. When it loses that 1 electron, it has 1 less electron, it gets the electron configuration of neon, so it has a full octet. Barium, it's the same, except it's got to lose 2, and then it has the electron configuration of xenon. So this is the deal with ions. Again, if you wanted to say, draw the Lewis structure of barium with a charge of +1. This would be very rare, but this is how you would do it. So barium starts with 2 valence electrons. When it has a charge just of +1, it means it's only lost 1 valence electron. And so you would show that remaining valence electron right there. Now, sometimes you'll have problems where they want you to show maybe a loss or a gain of electrons stepwise. So you might start with barium as a neutral atom with 2 valence, and then barium with a charge of +1 with 1 valence, and then barium with a charge of +2 with no valence, or again, you can think of it as a full outer shell. It just kind of depends on how your teacher or your professor is running your class. So just mimic whatever they are doing in class. Okay, any questions? Nope. Okay, good. It sounds like the mic connection has worked well. All right, so that is Lewis structures of ions. Of course, those are monoatomic ions, but we will do polyatomic ions, but not quite yet. So now for, I feel like, the real meat of this live stream. This is Lewis structures of molecules. So instead of just dealing with one atom, either a neutral atom or an ion, now we're going to bond atoms together. Okay, so we have rules for how to do Lewis structure. And this is how everyone's kind of got a little bit of a different way of drawing Lewis structures. These are my 3 steps for drawing Lewis structures. So my first step is I'm going to add up all my valence electrons. This is why I started with counting up valence electrons, because for the molecules, my first step is I'm adding up all my valence electrons of all the atoms in the molecule. My second step is I'm going to take my best guess as to what the structure of this molecule may be. So really, when I do this, I identify what the central atom is. And for these Lewis structures, especially when you're just in Gen Chem and we're not talking about all the Lewis structures in organic, you're going to have a structure where you're going to have a central atom and atoms bonded around it. So I'm going to identify that central atom, and I'm going to put all of my other atoms around that central atom. And then my last step, my step number 3 right here, is I'm going to start sharing pairs of electrons. Now, for 2 atoms to be bonded, they must share at least 1 pair, or they must share at least 2 electrons. So I always start with sharing 2 electrons between atoms first, and then I add in all of my remaining valence electrons. I know this is a little bit difficult. It makes more sense when we put it into practice. So let's start with an easy one. Let's start with methane. Okay, so my first step is I'm going to add up all my valence electrons. So how many valence electrons does carbon give me? Carbon gives me 4 valence electrons. Now I have 4 hydrogen atoms, so I'm going to have a multiplier of 4 here. Hydrogen itself only has 1 valence. Okay, so this is going to give me a total count of 8 valence electrons. I'll just write that as 8E. So that is how many electrons I have to work with. I can't draw a structure with 6 electrons. I can't draw a structure with 10 electrons. I must use 8 in my structure. Okay, next for my part 2, again, I'm going to sketch out what I think my best guess is for what I call the skeleton structure of my Lewis structure. And to do that, I need to first identify my central atom. And there are a couple of ways to do that. So very often your central atom is written first. Not always, but very often your central atom is written first. Another hint that is your central atom is there's only 1 of this atom. So I have 4 hydrogens, but only 1 carbon. So carbon is probably my central atom. So I'm going to draw carbon in the middle, and I'm just putting my 4 hydrogens around on the outside like so. All right. Now I need to make these atoms share electrons, and they must share at least 1 pair for a bond to form. So I'm going to put 1 pair of electrons between the carbon and each of these hydrogens. Now, notice how many electrons have I used? 2, 4, 6, 8. Those are my 8 electrons. I can't put any more in. Those are all the electrons I have. Now I want to make sure that octets are satisfied. All right, so if I look at the electrons around carbon, how many do I have? I have 2, 4, 6, 8. So carbon has its octet satisfied. Now I want to look at each hydrogen. So let's start with this one up here. So how many electrons around that hydrogen? There are just these two right here. You say, what? Hold on a second. Hydrogen does not have an octet. It doesn't have 8. It only has 2. But I need the periodic table. Let me go back to the periodic table. If we look at hydrogen right here, hydrogen and helium, their electrons are in that 1s orbital. Remember, this is 1s1 and 1s2. That orbital can only hold 2 electrons and then it is full. So for both hydrogen and helium, and you're probably going to be dealing with this mostly with hydrogen, 2 electrons satisfies its octet, even though it's not 8, because that fills its outer shell. So this hydrogen actually does have a satisfied octet. Okay, so let's check this one. How many electrons? 1, 2. Again, remembering hydrogen is the exception. That hydrogen is fine. This one as well, again, also has 2. And this one also has 2. So this is a valid Lewis structure. I have used all of my valence electrons. I haven't used more. I haven't used less. Every atom has at least a single bond, is sharing at least 2 electrons, and everybody's octet is satisfied. Now, if you want, you can draw this a little bit neater. You can draw it with your bonds. So every time you see one pair of electrons, you just draw one line. So it's going to look like carbon bonded to 4 hydrogens with what we call single bonds. Single bonds are sharing 1 pair of electrons, which is why we draw one line. Now, drawing it with your dots is still an absolutely valid Lewis structure. Again, check with what your teacher or your professor wants. Some don't want to see the dots unless if they're part of a bond. Others, it doesn't matter. So just mimic what you're doing in class. Let's do another one. Again, we're going to do a lot of these. All right, so let's do ammonia. Again, my first step is I'm going to add up all my valence electrons. So nitrogen gives me 5 valence electrons. I have 3 hydrogens. Each hydrogen gives me 1. So again, I have a total of 8 valence electrons to use. Let's identify central atom. Well, nitrogen is written first, and it's also all alone. So I'm going to put nitrogen in the middle, which means I'm going to put 3 hydrogens just around nitrogen. So again, this is my best guess. Now I'm going to start filling in electrons. Again, I'm going to start with putting 2 electrons in between all of the atoms that I want bonded. So I know I want nitrogen bonded to these 3 hydrogens. So I'm going to put 2 electrons there. So I've used 2, 4, 6 electrons. So I have 2 more electrons remaining. Let's first check octets. All right. So we have this hydrogen has 2 electrons. We know that's fine. This hydrogen also has 2 electrons, so octets are satisfied with all 3 of our hydrogens. But if we look at nitrogen here, you can see you only have 2, 4, 6 electrons. But the good news is we have another pair of electrons that we can use. Now, this is your first instance of having what's called either a lone pair or a non-bonding pair. I tend to call them lone pairs, but it's the same thing. So you can see now that nitrogen has 8 electrons around it. Its octet is satisfied. We've also used the 8 electrons that we have, which is something that's critical as well. So this is our valid Lewis structure. Again, I can draw this a little bit neater with nitrogen bonded to 3 hydrogens. And then don't forget your lone pair up here. So you must be sure to add in your lone pairs on any of the atoms that need lone pairs. Otherwise, people are going to look, especially your teacher is going to look at this Lewis structure and say, this is not valid. So if you had forgotten your lone pair, you would only actually have 6 electrons around that nitrogen, and that would not be valid. So don't forget your lone pairs. Okay, let's make sure there are no questions. All right, good. Hopefully these structures you're finding pretty easy, because we're going to get to some more difficult ones, but I like to start with the easy examples first. Okay, carbon monoxide. Let's add up our valence electrons. So carbon gives us 4 valence electrons, oxygen gives us 6, so we have 10 valence electrons to use. In this case, there is no central atom because we just have carbon bonded to oxygen. So I'm just going to write them next to each other like so. Okay, so I've got 10 electrons. This is kind of my guess as to how they're going to be because, you know, it's just carbon bonded to oxygen. And again, I like to start with sharing one pair of electrons. So we'll put our one pair right here in between carbon and oxygen. That's only 2 electrons. I've got 8 more to use. So now I'm going to start putting pairs of electrons around atoms until I run out. So this is 2 electrons, 4, 6, 8, 10. Okay, so that's all the electrons I have. Let's check octets. Okay, so around the carbon, I have 2, 4, 6, 8, so carbon is great. And then around this oxygen, I only have 2, 4. All right, so oxygen definitely is not going to be content to just have 4 electrons. So in this case, when you start with a single bond or just sharing one pair of electrons and you find that some atoms are short, then you need to make your atoms share more electrons. So right now my atoms are only sharing 2 electrons or one pair. So let's change that up. Let's erase my circles. And instead of just sharing one pair of electrons, let's make them share 2 pairs. And this is really the key, I think, with Lewis structures, is you take your first stab at it, you take your guess, and then you test it. Is this valid? Is this not valid? And then you change it up, and then you test it again. So don't feel like you have to jump into knowing what the Lewis structure is at first. You're going to do a lot of guess and test. Okay, so to make them share more, I'm going to erase a pair of electrons from carbon, and I'm going to put it in the middle. So now they're sharing 4 electrons. Now, before I check octets, I want to make sure that I still have 10 electrons in this drawing, because when you start erasing pairs and moving them, it is very easy to either accidentally add a pair in or remove a pair. So I just want to check. I've got 2, 4, 6, 8, 10. I still have 10 electrons. Okay, let's check octets. Okay, carbon still has 8 electrons. That's fine. Oxygen's octet is not satisfied, but it's better, right? So instead of having 4 electrons, it now has 6. So we've made progress towards satisfying oxygen's octet. So instead of sharing just 4 electrons, let's make them share more. Let's share 6 electrons. All right, so let's erase here. Eek. I'm going to have to redraw some of those electrons. Okay, so 2, 4, 6. Check and make sure you have 10. 2, 4, 6, 8, 10, 12. Uh-oh. What did I forget to do? I forgot to erase a pair of electrons before I put it in the middle. This is why you always check. It's very easy to do. Again, guess and test and guess and test. Okay, so now we have 10 electrons. Let's check octets. All right, so around carbon, I have to get kind of close here. We still have 8, so we've got 6 bonded in between carbon and oxygen and 1 lone pair. That gives us 8. And oxygen also has now 8 electrons. Its octet is satisfied. This is our valid Lewis structure. Now, if you don't like all the dots in between, that's fine. This is called a triple bond. And don't forget your lone pairs. Now, I like to draw my lone pairs like this, but up in this structure, I had my lone pair and oxygen on top. It's totally fine. Put it wherever you want. Just make sure it's paired together. So what you don't want to do is you don't want to draw your 2 extra electrons like that. We always keep our electrons in pairs. So just make sure you keep the electron with its buddy, right? So these are seat buddies. They stay together. Keep your electrons in pairs. Okay, that's carbon monoxide. Let's do carbon dioxide. All right, so first step, count up valence electrons. So carbon gives me 4. I have 2 oxygen. They each give me 6, so this is 12. And 4 is 16 valence electrons. Yes, okay. All right, start with my central atom. It's going to be carbon. Again, it's written first. It's the single. We have 2 oxygens, so those are probably not going to be central. So I'm going to put carbon in the middle, and I'm going to put oxygens on either side, or maybe in this case, instead of oxygens on either side, I'll put the oxygen on top. It doesn't matter. Just put them around your carbon and give yourself enough space that you can put electrons in. Okay, so let's now put our electrons in. We want to make sure that everything shares at least 1 pair or 2 electrons. So I'm going to start with that. So I need to make sure I form a bond between carbon and both of these oxygens. So I've used 4 electrons. I'm just going to start adding in electrons until I hit 16, and then I'm going to check octets. So we have 2, 4, 6, 8, 10, 12, 14, 16. Okay, those are all my electrons. So I'm done. I can't keep adding electrons. And that's another mistake that I commonly see made is you start drawing in electrons on your structure, and you just keep drawing electrons in because it's so easy, right? They're just little dots. But make sure you stick with how many valence electrons you have. All right, so let's check octets. I'm sure at this point you can tell octets are not going to be satisfied, but that's all right. We'll go through our proper test. Okay, so that oxygen has 8. We're fine. Carbon here has 8. It's also fine, but we have a problem with this oxygen right here. It only has 4. So that octet is not satisfied. So what do we need to do? What did we do in carbon monoxide? We made them share more, right? So let's make them share more. Okay, so trying to erase my circles is getting to be a little bit difficult. All right, so I am going to erase this pair of electrons. Eek. And I'm going to make these guys share. All right, so let's check my atoms. This oxygen here still has 8. It's fine. This carbon also has 8. That's great. And this oxygen now has 6, so that's fantastic, but it's still not quite there yet. Okay, so we need to make them share more. So I am going to take, let's see, if I take these 2 electrons, all right, so let's try this. What if I were to put them right here? Okay, so let's make a triple bond here. Is this a valid Lewis structure? So again, make sure you have 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we've got 8 around this oxygen. We have 2, 4, 6, 8 around this carbon, and we also have 8 around this oxygen. Now, this might be a Lewis structure of carbon that you're less familiar with because you're probably used to carbon dioxide having a double bond. So this is where you can have more than one valid Lewis structure, and it just depends on how deep your class goes into Lewis structures. But we have used 16 electrons and everybody's octet is satisfied. Now the problem here is we've actually got some formal charges which make it a less likely Lewis structure. So if we're trying to, let's say, make this symmetrical, then let's move some electrons around. Let's take this pair and bring it over here so that each oxygen has 2 lone pairs. But that means this oxygen has too many. So instead of sharing 6 here, let's share 2. And let's share 2 right here. Can you guys see that? All right, these dots get a little bit crazy. So what I've got now is I've got a symmetrical molecule, and I actually don't have any formal charges. I'm not going to get into calculating formal charges right now because some classes do this and some don't. But what this does is it means you have carbon with a double bond to oxygen with 2 lone pairs, and then with another double bond to oxygen, and I'll put my lone pairs on the side here. And this is probably the Lewis structure of carbon dioxide that you are more used to seeing. Again, this ties into formal charges. But check and make sure, have you used 16 electrons? 2, 4, 6, 8, 10, 12, 14, 16. Yes. Does everybody have 8 electrons? This oxygen has 8, carbon also has 8, and this oxygen here also has 8. So this is also a valid Lewis structure. And we are going to run into this later as well, where there might be multiple versions of valid Lewis structures. Okay, any questions about this? Nope, let's keep on going. So we've got more Lewis structures to do. Okay, so here are ones that are a little bit more difficult to handle. We're still using the same rules for Lewis structures, and we're still going to use the same method, so we're going to work through this very systematically. All right, let's start with this structure right here. Okay, and to save space, I'm going to start using the lines for bonds instead of drawing all of the dots. But let's add up valence electrons first. Okay, so carbon gives me 4 valence electrons. Oxygen gives me 6. I have 2 chlorine atoms. So I'm going to have 2 times the valence electrons of chlorine are 7. Okay, so I have got 14 and 10. I have 24 valence electrons. So I've got a lot of valence electrons. Okay, now I need to make my best guess as to the structure of this Lewis structure. Remember, I want to find my central atom. My central atom is probably going to be written first, and it's going to be a lone atom. Well, you can see I have carbon and oxygen are both lone atoms, but because carbon is written first, that is going to be my central atom. So I'm going to have carbon, and I'm going to have 1 oxygen and 2 chlorines around it. So the temptation with these structures is to take a guess where you're going to do carbon, oxygen, and chlorine. But remember, you're always going to have a central atom and atoms bonded around it. So guessing this structure first is going to be very difficult because you don't have a central atom with atoms bonded around it, because these atoms are all just linearly bonded. So just remember, when you're taking your best guess, this is why we identify our central atom and then put all of your other atoms around it. Okay, so I have 24 electrons. I always like to start with single bonds. Okay, so single bond here, here, and here. That's 6 electrons that I've used. I have 24, so now I'm just going to start adding in electrons until I run out. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so that's how many electrons I have. I can't keep adding electrons. Let's see octets. All right, so this oxygen right here, yes, that has 8. Some of these electrons have holes. Carbon right here also has 8. That's fine. This chlorine has 8. That's fine. Then this chlorine only has 6. So we've got a problem. All right, so what we need to do is we need to give that chlorine 8 electrons. So I'm going to erase this pair, and I'm going to give it to chlorine. Okay, so now that chlorine is totally fine, right? Okay, so we have 8, we have 8, we have 8, but oops, now our carbon only has 6. Again, don't be afraid to take a guess and test it. So what we've got is we've got, most of our octets are filled, but not all of our octets are filled, which means we need to make our atoms share more electrons. So let's take this pair from oxygen and let's make a double bond. Again, make sure you still have 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we have not created or destroyed electrons. Now let's check octets. So this chlorine, yes, has 8. This chlorine also has 8. Oxygen still has 8, and now you can see that carbon has 8 as well. So that double bond, that sharing of 4 electrons instead of 2, has made it such that everybody's octet is satisfied, and here is our valid Lewis structure. Okay, let's go on to our next one, PFCl2. Again, this one looks kind of crazy, but we start with our step 1 always. We just add up our valence electrons. So don't worry if a molecule looks really weird or you don't know what it's going to look like, just start with your first step and then let each step come as it needs to. All right, add up valence electrons. So phosphorus gives us 5. Fluorine gives us 7. We've got 2 chlorines, and chlorine also gives us 7. So what we've got is we've really got 28, 32 valence electrons. Okay, identify our central atom. Again, both phosphorus and fluorine are alone, but phosphorus is written first, so I'm going to put phosphorus as my central atom. And then that means I have 1 fluorine and 2 chlorines around it. Okay, so this is my first best guess as to my Lewis structure. Let's start with single bonds and let's see if we can satisfy octets. Okay, so single bonds between each of these guys. So I've used 6 electrons. I'm just going to keep adding until I've used 32. So that's 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Whoops, have I added up my electrons wrong? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I must have added, oh, of course I did. This is 14, this is 21. I have 26 electrons. Sorry, I couldn't do my addition multiplication correctly in my head. All right, so I do have 26 electrons that I have put in here. Otherwise, we'd have to do expanded octet, which I'm not going to do in this live stream. So let's check and make sure everybody's octet is satisfied. All right, so we have fluorine here with 8. Yes, it is satisfied. Chlorine here also has 8. Great. This chlorine on the left also has 8. So we finally check phosphorus, and it also has 8 because it's got this lone pair right here. So this is our valid Lewis structure for PFCl2. Okay, we are kind of running short on time, and I definitely want to get to the polyatomic ions. So I am going to leave a sulfur dioxide and COS to you guys. Let's go ahead and move on. Let's do our polyatomic ions. Our rules stay the same, but again, just like when we did our monoatomic ions, our number of electrons changes. So I'll show you how this works. We'll start with the ammonium ion. So adding up our valence electrons, nitrogen gives me 5. I have 4 hydrogen. They each have 1. Now remember, when an ion has a positive charge, it means it has lost an electron. So I am going to subtract 1 from my count, which means I have 8 valence electrons. Okay, so this is how we count valence electrons for, also for monoatomic ions, but for polyatomic ions. You look at the charge. If you have a positive charge, it means you've lost electrons, so you're going to subtract out whatever the charge is. If you have a negative charge, it means you've gained electrons, and you're going to add electrons in. Okay, so we have 8 valence electrons. We still go on to our second step. Let's find our central atom. Well, nitrogen is written first, and it's all alone, so it is our central atom. So we have nitrogen here, and I am just going to draw 4 hydrogens around. And now I'm, like always, I'm going to start with single bonds. So 2, 4, 6, 8. Those are my electrons. That's all I got. Let's check octets. So you can tell nitrogen here does have 8 electrons around it. That's fine. Remember, hydrogens only want 2. So each of these single bonds for hydrogen satisfies its octet. This is the valid Lewis structure. That's it. So that one was actually pretty easy, which is why I like to start with it. Okay, so let's check, let's see, that is chlorate. And again, it has a charge, so this is going to change how we add up our valence electrons. So chlorine has 7 valence electrons. We have 3 oxygen. They each have 6. And again, we have a negative charge, which means we have gained an electron, so I'm going to add 1 because its charge is -1. So this is 24 electrons. You guys check my math because obviously it's not always correct. Okay, so let's sketch out our arrangement of atoms. Chlorine is going to be my central atom. It's written first. It's alone, so I'm going to put a chlorine here, and I'm going to put oxygens around it. So a lot of times you get used to seeing your halogens on the outside, but halogens don't have to always be on the outside. In this case, it is a central atom. That's totally okay. All right, so 24 electrons. I'm going to start with single bonds. 2, 4, 6, and now I'm just going to add electrons in until I've used up 24. So this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so that's all I got. Let's check octets. All right, so oxygen here on the left is good. The lower oxygen also has 8. This one on the right is fine, but chlorine only has 6. So I need to make them share more electrons. So I'm going to erase that pair right there, and I'm going to make this a double bond. Again, make sure you've used 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes, we've used 24 electrons. Check octets. This has 8. Yes. This lower oxygen also has 8. This one on the right, 2, 4, 6, 8. And chlorine now has 2, 4, 6, 8 electrons. So octets are satisfied. Okay, so the thing that I want to point out about this, because I know I'm running out of time, is let's say, you know, you're working in a group and you turn to your neighbor next to you and you can see that they have written or drawn this Lewis structure. So it still has 24 electrons, but you've got the double bond in a different place. Is that okay? Yes, that's perfectly okay. These are called resonance structures, and you often draw the double-headed arrow between resonance structures. So again, kind of like we saw previously, you can have more than one valid Lewis structure. You need to make sure you use all of your valence electrons, and you need to make sure everybody has a satisfied octet. Now, depending on your class, you might have to bring formal charges into effect, but usually on the Gen Chem level, those are the only things you are looking for. So again, you might have more than one valid Lewis structure. Okay, before we go, I do want to go to this very last page, and I at least want to do some of these. Let's do one. Let's do maybe carbonate right here. Okay, so because it's got a charge of -2, so let's practice with that. So I'm going to add up my valence electrons. Carbon gives me 4. I have 3 oxygen. They each give me 6. We've got a negative charge, so I'm going to add electrons in, and because I have a negative charge of -2, that means I'm adding in 2 more electrons. So what I've got is I've got 18 and another 6, so I've got 24 electrons again. This seems to be a theme, so I think you can probably see where this is going. Again, carbon is your central atom, is written first, it's alone. Hopefully as we do these, you're seeing a pattern with these. Okay, so starting with single bonds. Bam. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm out of electrons. Okay, let's check octets. Carbon has 8. That's great. Oxygen on the right has 8, the lower oxygen has 8, and our one on the left only has 6. I need to make them share more electrons. Now, I'll show you a common mistake that's made where you can kind of get stuck, is maybe you erase this pair and you make it share more here. So what is the problem with this? Well, there are 2 problems. First of all, this oxygen right here still only has 6 electrons, so you haven't increased its number of electrons. And now take a look at the carbon right here. It has 2, 4, 6, 8. It has 10 electrons around it. So this is why, again, we guess and we test. So that actually took us farther away from our goal instead of getting us closer to our goal. So we go back to our original structure because that one was actually closer to our goal. Okay, let's do another try that you might do. You might take one of these electrons, these pairs, and say, I'm going to put it right there. Again, I still have 24 electrons. Now this oxygen has 8. That's great, but we have another problem. This oxygen now only has 6 electrons. And again, your carbon here is ending up with 10 electrons. It can't handle 10 electrons. So again, this is why we guess and test. You can say, every time I take a pair of electrons from an oxygen and I make it a double bond, I end up with carbon with too many electrons. So let's go back again to our original structure that we tried first. And instead of taking a lone pair from oxygen, let's take the lone pair from carbon. So let's pull this one out and let's make it a double bond with that oxygen. Okay, so now check, and you can see that carbon only has 8 electrons, which is what it needs. This oxygen now has 8. And both of these oxygens here also have 8. So again, don't be afraid to guess something and try it. But if you find that it's taking you farther away, like when we had 10 electrons around carbon, but that oxygen still had 6, go back to where you started from and try something completely different. The other piece of advice that I will also give is if you find yourself really stuck and you just keep spinning your wheels and you're finding all of these wrong structures, sometimes it helps to just turn the page over, start over fresh, and do the structure fresh. Or if you've got the time, like if this is just a homework set, go take a break. Go take a 10, 15-minute break. Go do something else. Go study another class or do other homework. And again, come back to that Lewis structure completely fresh, because sometimes we get stuck in a cycle of these wrong Lewis structures. Like you could see with this carbonate structure, if you kept trying lone pairs from oxygen, you would keep getting wrong structures, and that can be very, very frustrating. And again, sometimes you need to put it aside and leave it and come back and go, wait, what if I took that lone pair from carbon? Like that's the thought that needs to come. So again, if you have the time, if you're just working on homework and you can leave it and come back, that's also a good strategy for just trying to figure out Lewis structures. Okay, so yes, it is 8 o'clock. Oh, we've got some question 32. Yes, I totally got my math wrong. I'm not sure why your comments didn't come through sooner. Oh, check the microphone connection again. I'm so sorry. Besides hydrogen and helium. Oh, would you say this is high school or college level Gen Chem? So Jessica, those are great questions. Yeah, so sorry about the math. But this is really both high school and college level. So maybe in high school you might not do polyatomic ions. You might just stick with the really simple Lewis structures. So I would say generally in college you're going to do the more difficult structures like the carbonate with the charges and the ions. Also, the other thing that sometimes you find in high school classes is you'll find an expanded octet. So in all of these structures, we only did octet rule. So every atom had 8 and you didn't have more. But you can also have expanded octet structures. And that's something that maybe we could even do next week, is do the expanded octet. And that's something you're going to play with a lot more in college. And if you take these Lewis structures and then you predict molecular geometry based on VSEPR, again, you're going to have a lot more shapes like octahedral and T-shaped and square planar and square pyramidal and all of those shapes as well. So we really do see this in both. I think it's just the level of the class. Like, are you taking 10th grade intro level chemistry, or are you taking AP chemistry or IB chemistry? You might see some more. So it really depends on the class, and it also depends on the teacher. Okay, it really depends on that. But you'll certainly always see first the neutral atoms, then the monoatomic ions, and then the really, really simple compounds as well. Okay. Oh, comment in the exceptions to the octet rule. Yeah, absolutely. So I can actually show you one really quickly. So I'm going to kind of cheat on sulfate. So sulfate, you can draw this by just using octets. But sulfur is a third row element. So it can actually take an expanded octet. Now, this drawing right here is sulfate with just following the octet rules, but what we find is probably the more accurate structure for sulfate, oops, I forgot those there, is to do double bonds right here. So if you look at sulfur, you can see it has 2, 4, 6, 8, 10, 12 electrons around it. So this is an expanded octet. It is more than 8. This works with sulfur because it is in the third row, which means it can start putting electrons in that empty 3d orbital. If you're talking about carbon or oxygen or nitrogen, they have no ability to do expanded octet. So trying to, like when we were down here and we had carbon with a lone pair and we had 10 electrons, carbon doesn't have anywhere to put those. It will never have an expanded octet. Now, if you have a carbocation, it might only have 6, but again, that's really more organic chemistry. I wouldn't worry about that. But this is an example of sulfur having an expanded octet. But there's so much more that we could go into. Again, if you want to see more examples of expanded octet and how you handle that, like we can totally do that. And we can even do molecular geometry if that's what you're working on as well. But there are a lot of ways that we can take this. So just third row and below, yeah, just third row and below, because it's got to have access to those d orbitals. So your first row, your hydrogen and helium, they only have the 1s, so like they max out at 2. And then your second row max out at 8 because they have no d orbitals. The d orbitals don't start until the 3ds, which is why you've got to be in that third row and below where you have access to those d orbitals where you can stick those extra electrons in. But the second row, the atoms are they just aren't big enough. Okay, yes. Oh, okay. I can relate to that. It's totally fine. Yeah. Well, I appreciate all your questions. Like, I'm always happy to answer any questions, and hopefully this clarified some Lewis structures for you. They can be difficult because again, you have to guess and then you test and then you guess again and then you test, and it can get really frustrating when you have to keep guessing. But I promise it does eventually work. You just have to keep plugging away at it. And again, the more examples you see, then you're like, oh, I tend to see like oxygen tends to have double bonds and 2 lone pairs a lot. Yeah, that happens a lot. So you start to recognize like small subtle patterns in between there as well. Okay. All right. Well, I'll let everybody go. Thank you so much for joining me on this live stream. Again, if you have requests of different topics that you want to see, please let me know. I'm happy to do whatever topics you're most concerned about or you're working in class. And I hope to see you guys next week. Bye.